Let's consider this problem that we discussed in class. Historically, an average of 3,218 people have entered a certain store. A redesign of the store shows that in a sample of 45 days, there's been an average now of 3,392 people coming to the store, with a sample standard deviation of 287. The question is, at the 0.05 level of significance, does this indicate that the average number of people entering the store has increased daily? To get started on this, we first recognize that this is a problem about the parameter mu, the average, and we're going to perform a hypothesis test on this to determine whether or not the average has indeed increased. That is when we typically use hypothesis testing. It used to be this way. Something has changed, and because something has changed, has there been an increase or decrease or a change in the parameter of interest? So to get started with this, we note that the null hypothesis is going to be that the mean has remained 3,218. In other words, we kind of play devil's advocate here. There has been an increase, but the increase is attributable to chance. We like the new storefront entrance, but the increase is simply due to just a good run of luck, and that the real population mean is still 3,218, even though the sample average is a little bit larger than that. The alternate hypothesis in this problem will be that the average is a real increase, or the average is really increased, that mu is greater than 3,218. I've got a very nice storefront entrance, and so I think that because of that, that has caused an increase. So notice that mu is greater than 3,218. The other possible option would be not equals to in this problem. I do not choose that option because I think that the storefront redesign worked, and so if there's a change, I think that there's an increase. The next thing that we do is work with the test statistics z, and the test statistics z from the central limit theorem is going to be equal to the sample average minus the mean divided by the, well, it should be sigma divided by square root of n. According to the central limit theorem, this will follow the normal curve. In our problem, we do not have sigma. What we do have is the sample standard deviation s. And so because I have a large sample, I've got at least 40, a sample of size at least 40, in this case 45, it is safe to approximate sigma by s. So using the guidelines that we discussed in class and from the textbook, we know that x bar minus mu over s over square root of n is approximately normally distributed. If n is not large, then we have to use something called the t-distribution, which we will discuss in a later video. Okay, so for this particular problem, let's go ahead and do the calculation here. X bar is equal to 3,392. That's our sample average. Under the null hypothesis, the mean, the true population mean is 3,218. And then I would divide this by 287 divided by the square root of 45. And so doing the arithmetic, we get 4.06699 accurate to 5 decimal places. That's probably more accuracy than is necessary for this problem. But that is the value of the test statistic. Next step is we figure out if that makes sense or not. So what we've got here is that if we believe the null hypothesis, then a logical consequence of believing the null hypothesis is that we just got a test statistic of 4.067, so a little bit more than 4 standard errors above expected. This is possible. The question is this, plausible? To determine if this is plausible or not, the technique we'll use is to find the critical value and the rejection region. So in this case, we're given that there is the level of significance right here is 0.05. So we need to use the bell curve to determine the level, the critical value that goes along with that level of significance. So let me draw the bell curve over here. So I need to figure out the value of z critical, so that the area to the right is equal to 0.05. and it is the area to the right because we have the alternate hypothesis as mu greater than 3218. So I have a greater than sign for the alternative hypothesis, which means that I need to use a right tail test for the bell curve. Okay, so for this we use either the calculator or Microsoft Excel. I'll use Excel. So we have norm Sin of 0.95. 95% of the area must lie to the left, so that 5% of the area lies to the right. So 1.64485. .64485. And that is going to be my cutoff for deciding whether or not to retain or reject the null hypothesis. So on this side, my decision is to retain the null hypothesis, that I got a number that was not large enough for me to think that the null hypothesis was not plausible. On the other side, my decision will be to reject the null hypothesis. In other words, I got a test statistic that is so large that I don't think it's plausible for the null hypothesis to be true, and so I decide to reject the null hypothesis in favor of the alternative hypothesis. So that's the critical value determines my cutoff for where I think that boundary is. Determines my cutoff for making that decision. So in our case, we have 4.0669 that clearly falls in the rejection region, and so our decision will be to reject the null hypothesis. And so let me go ahead and type that in. So our decision is that we reject the null hypothesis. Then we state the conclusion words. There is good reason to think that the average number of customers is larger because of the redesign. So based on the size, the test statistic, we make this decision. Now, of course, we have made a decision. We are not 100% certain that we have made the correct decision. It is perfectly possible to get a test statistic that large. After all, there still is area to the right of 4.06699. So that would be an example of what is called a type 1 error, where we have simply made the wrong decision, where we have rejected the null hypothesis, even though the null hypothesis is correct. However, we have a good reason to make the decision that we've made, even though we cannot be 100% certain that we've made the correct decision. And that's kind of the unfortunate thing about statistics, is that we can never be certain that we've made the right decision, even though we've made a decision that we think is rational and defendable.